Welcome back everyone to another video in our Fundamentals of Structural Engineering course. In this video, we are going to learn about moving loads. There are different forms of moving loads that could affect any structure. One of the most common type of moving loads are vehicle loads, which could be on a bridge or on a road or any other structure. Another form of moving loads, which is crane loads, which is also a moving load along the crane girder. In this video, we are going to learn how to calculate the maximum effect of any moving load, either single load or double loads or any other combination of loads. First thing we are going to learn here, which is single loads. If we have this single moving load here, P, on any beam here, and we want to calculate at which location this load is going to have the maximum moment and the maximum shear, it makes sense, and I believe it is very simple, that the maximum moment will be when the load is in the middle of the span. So this is the maximum, or this is the worst location for the moment, and the moment in this case equals PL over 4, and it happens when the force is in the mid of the span. And the maximum shear effect, it happens when the load is exactly on top of the support here, either this support or this support, and the value of the shear will equal P, which is the load itself. So what about if we have two moving loads? In case of two moving loads, as we can see here, we have PB and PS, considering that PB is the bigger load and PS is the smaller load. In this case, to find the location where this load is going to have the maximum effect on the beam, we need to calculate first the resultant of these forces, and we can find the location. Here we can have the P, which is the resultant of the PB and PS, where P equals PB plus PS, and we need to find the location of this P, and based on that we will align our forces so that the center of the beam is exactly in the center between the resultant and the big load. As you can see here, this is the center of our beam, and this is the resultant, and this is the big load. This exactly should be in the middle. In this position, this load system is going to have the maximum moment on our beam, which is going to equal P multiplied by L minus P small multiplied by D all squared all over 4PL. But the most important part here is that you need to find exactly the location to apply these forces. And to find that, you need to calculate first the resultant, you need to find the location of the resultant, and you need to align your system of loads to be exactly in the middle between the center of the beam, to be exactly in the middle between the big load and between the resultant. And the maximum shear will happen when the big load is exactly on the support, and you can find the value of the shear using the equation of equilibrium. And always in this case, I forgot to tell you that the maximum moment will be under the big load here. This means that this point will have the maximum, this point here will have the maximum moment on this beam. So in general, if we have 3 loads or even more loads, in order to find out the location of the effect of that is going to have the maximum moment on our beam, we need to find the location of the resultant of this loading system, and the distance between the beam midpoint to the resultant should equal the distance between the beam midpoint to the biggest force. And for the maximum shear, we need to find the location where the resultant should be as close as possible to the support. So now, let's have an example on this. So here we have this example. It says a system of 3 loads roll across a 44 feet beam. The loads are P1 equals 4,000 pounds and P2 equals 8,000 pounds separated by 9 feet, and P3 equals 6,000 pounds at 18 feet from P2. The maximum moment is most nearly, and we have 4 options here. First, we need to allocate this system of force. We have 3 loads, P1, P2 and P3, with these values given here, 4,000, 8,000, 6,000. But we don't know where exactly this system of loads is going to be applied, because this system of load is moving here we want to find the location where it is going to have the maximum moment on this beam. In order to do that, as we learned, first we need to allocate the system on our beam here to find the maximum effect, and in order to do that we need to calculate the resultant location. So we'll start first, we will take this system of forces here of 4,000, 8,000, 6,000 with these dimensions or with these distances. The resultant is going to equal 4,000 plus 8,000 plus 6,000, which means the resultant equals 14,000 pound, and it is going to be here. We need to find exactly what is the location of this resultant force. So we are going to take sigma of the moment at this point here, point x. So if we take sigma moment at x, this means that 8,000, which is this force, multiplied by 9 plus 6,000 multiplied by 27 should equal the resultant, which is 14,000 multiplied by x, which is this distance here. So we can find from here that x equals 13 feet. So the distance between 4,000 to the resultant equals 14 feet. And we know that this distance is 9 feet. So this distance here equals 4 feet, which is between the big load and the resultant. We know that in order for this system of loads to have the maximum effect, the center of the beam should be exactly here, in the center between the big load and between the resultant. So now we can allocate our system of forces on our beam. So it is going to look like this. We have our beam here and we have the 3 loads here allocated so that the distance between the 8,000 and the center of the beam is 2 feet, because the resultant is will be on another 2 feet from here. So this will be the location of the forces. Now we just need to calculate the reactions of RB and RA. You can find these dimensions easily. This dimension here is 2 feet and the total distance here is 22. So this distance is 20 and the distance between 4,000 and 8,000 is 9. So the remaining is 11. It is very simple. Now you just need to calculate the moment at one support to find the other reaction. So sigma moment at A equals 0. This means 4,000 multiplied by 11 plus 8,000 multiplied by 20 plus 6,000 multiplied by 38 equals RB multiplied by 44, which means RB equals approximately 9,800 pounds. And based on the total summation of forces at Y direction, we can find that the RA equals 8,200 pounds approximately. So we can just calculate the moment at the 8,000 force here at this point, which is going to equal 8,200 multiplied by this distance, which is 20, minus 4,000 multiplied by 9, which is going to equal approximately 127,000 pound-foot. So this is the answer, which is the fourth option, number 4, 127,000 pound-feet. So this is it for our video today. See you in our next video. Thank you.